Welcome to Class Time, your daily classroom for CSEC and CAPE subjects. It's now time for CAPE Chemistry. I am Ricardo Price. Today's lesson, we're going to look at atomic orbitals and periodic trends. So, the objectives for today's presentation, taken from the CAPE syllabus, will be required to describe atomic orbitals. We'll also be required to know the shapes of these orbitals, electronic configurations, and the occupancy of these orbitals. We'll also be required to know ionization energies and how it provides evidence for the existence of these orbitals. We'll also be required to know the factors that influence ionization energies and to use ionization energy data to derive electronic configurations. So, let's start with the electronic configuration and atomic orbitals. Now, last week we spoke about the Bohr model, and the Bohr model describes a system where you have a nucleus and electrons are orbiting that nucleus. But according to the Heisenberg uncertainty principle, it is impossible to know the exact position of that electron that is orbiting the nucleus. But it is possible to predict with a high probability the area where it is very likely to find an electron, and that area is what we call an orbital. Now, there are different types of orbitals. You have the s orbital, you have the p orbital, the d orbital, and the f orbital. And later on in this presentation, we'll describe the shape and how much electrons each orbital can hold. Now, bear in mind, these orbitals aren't physical orbitals. As I mentioned before, they're just the space or the area where there is a high probability of finding an electron. Now, let's start with the s orbital. So, with the s orbital, it's a spherical in shape. The s orbital is spherical in shape, as you can see, and it holds a maximum of 2 electrons. The p orbital, on the other hand, there are 3 of them. Each p orbital can hold a maximum of 2 electrons. And since there are 3 of them, all 3 p orbitals combined can hold a maximum of 6 electrons. It's in 3D. You have 3 different p orbitals. You have the px, py, and the pz. What that means is that the px orbital, it lies in the x-plane. The py orbital, it lies in the y-plane, and the pz orbital, it lies in the z-plane in the 3D representation or the 3D model. They also describe the shape of the p orbital as dumbbell shape. You know a dumbbell, a weight that you use in the gym? It has the shape of a dumbbell. Now, we have the d orbital. There are 5 of them, and each d orbital holds a maximum of 2 electrons. And since there are 5 of them, the d orbitals combined can hold a maximum of 10 electrons. Now, the d orbital is similar to the p orbital in that it's like 2 p orbitals crossing, and you have the dxy orbital, which is basically the orbital that lies in the xy plane. It's a 3D representation. You have the dyz and you have the dxz, right? And as the name suggests, it lies in the xz plane. Now, you also have the dx squared and the dy squared. That means that the orbital lies directly on the z plane. That's dz squared. It lies directly on the z plane. And the dx squared, y squared lies on the x plane and the y plane. Now, the shape of the f orbitals are a bit complicated. So you guys aren't required to know the exact shape of these orbitals. You guys aren't required to know the exact shape of these orbitals, but you're required to know how many orbitals exist and the occupancy. No, there are 7 f orbitals. Each can hold a maximum of 2 electrons. Therefore, the f orbitals in total can hold a maximum of 14 electrons. Now, the s orbital is lowest in energy, and it occupies the first energy level. So on the first energy level, you have a 1s orbital. It is the only orbital there. There are no p orbitals on the first energy level. So if we take a look here, you have the n equal 1 energy level, and you can see that there is only a 1s orbital there. At the n equals 2 level, we have the introduction of a p orbital now. So if we are putting electrons in an atom, we'd start with the 1s. As we said earlier, an s orbital can hold a maximum of 2 electrons. Now, we put in the 2 electrons. Once this orbital is full, we move on to the 2s, and we put in the electrons in the 2s. Once we put the electrons in the 2s and it's completely full, we would then move on to the 2p orbital. Once we put in our 6 electrons in the 2p, we then move on to the next energy level, which is n equals 3. And then we put in the electrons in there. Now, at the n equals 3 level, we have the introduction of the d orbital. This signifies that the d orbital has a higher energy than the p and the s orbitals, right? Because it comes into play at a higher energy level. At the n equals 4 level, we have the introduction of the f orbitals, which are higher in energy than the d orbitals, the p orbitals, and the s orbitals. And that's how you fill out the orbitals in atoms when you're adding electrons. Now, just to recap, you can see that the s orbitals hold a maximum of 2 electrons, the p orbital holds a maximum of 6, and the d orbitals hold a maximum of 10. And the f orbitals holds a maximum of 14. It is important to know the maximum occupancies of these orbitals, because when you're writing the electronic configurations, you'd be required to know them. Now, let's do an example. For instance, we have the helium atom. Helium has 2 electrons, right? Therefore, if we're going to write the electronic configuration of helium, we'd have to represent it like this. The first number that you see represents the energy level that you're working with, the n level. So n in this case would be 1, the first energy level. The letter describes the orbital that the electrons are in. And the superscript with the number, that represents the amount of electrons within that orbital. So the electronic configuration of helium is 1s2. Let's look at another one. So we have the lithium atom. Lithium has 3 electrons. The first 2 electrons have to fill out the orbital that is on the first energy level, which is the 1s orbital. Once that is completely full, we then move on to the second energy level. And the first orbital on the second energy level is an s orbital. So we place the electron in that 2s orbital because we're now on the second energy level. Let's look at another. Now, we have boron. Boron has 5 electrons. So the electronic configuration would be 1s2, 2s2, 2p1. So now we have the introduction of the 2p orbital. And the more electrons you have, so the bigger the atom, you have more energy levels coming into play and different orbitals. Let's now look at sodium. Sodium uses the third energy level. Sodium has 11 electrons. So if we're going to place these 11 electrons in the orbitals, we'd have 1s2, 2s2, 2p6, and 3s1. Now, the 3s orbital comes into play here, and it would look something like this. So you can see the 3s orbital. All the s orbitals are spherical. So the first, for instance, with helium, which only has a 1s orbital, it would look something like this with the nucleus in the center. So you'd have the s orbital surrounding the nucleus. With the 2s orbital, like with lithium, you'd have the 2s surrounding the 1s, like so. With sodium, that has a 3s orbital as its outermost orbital, you'd have the 3s surrounding the 2s and the 1s. You'd have all these orbitals within this structure. So you'd have the 2p orbital within the 3s. Now, let's take a look at the board. So, it would look something like this, where you'd have, if this in the center is the atom, you'd have the 1s surrounding that atom. This would be the 2s orbital. This is the 2s surrounding the 1s. And then you'd have the 2p sticking out of the 2s orbital, right? And then you'd have, pardon my penmanship, by the way, and then you'd have the 3s surrounding the 2p, 2s, and 1s like this. Right. Now, writing electronic configurations can be a bit tedious, but there are alternate ways to writing these electronic configurations. I should note that the noble gas electronic configuration is very stable. It consists of a completely filled valence orbital. For example, the helium atom, the valence energy level in helium is the n equals 1 level. And it has an orbital that is completely full, so it's stable. Neon is another noble gas. And its valence energy level is the n equals 2 level. And its orbitals at that n equals 2 level are completely full because the s has 2 electrons, the p has 6. Thus, it is very stable. So we can write these noble gas configurations as the noble gas within a square bracket. So this configuration, 1s2, can be written as helium in a square bracket. And the neon electronic configuration can be written as neon in a square bracket. Now, we just did the electronic configuration of sodium. And we said that this is the electronic configuration of sodium. 1s2, 2s2, 2p6, 3s1. So it's kind of long in a sense. So I want you guys to make note of this. From here to here, this portion is the noble gas electronic configuration. And it looks just like that of neon. So instead of writing all of this, we could just replace this part with this, like this. So instead of writing all this, we could just write the electronic configuration of sodium is neon square bracket 3s1. So this would represent the electronic configuration of sodium. And you can do this for all your elements. So that's a quicker way how to determine or deduce your electronic configurations. Now let's look at the relative energies of these orbitals. Now let's start with the 1s, because the 1s orbital is the lowest in energy. You can see that there's a clear energy difference between the 1s and the second energy level, the third energy level, and the fourth, so on and so forth. So after the 1s, you have the 2s and the 2p orbitals. You see that the 2p is slightly higher in energy than the 2s. Then you have the 3s and the 3p. And at the third energy level, we have the introduction of the d orbitals, which are higher in energy than the 3p and the 3s. Now, at the fourth energy level, we have the 4s, the 4p, the 4d, the 4f. The 4f and the 4d aren't shown here because I want to highlight something. So although you guys know that the fourth energy level is higher in energy than the third energy level, which makes sense, but some of the orbitals within the fourth energy level actually have a lower energy than orbitals in the third energy level. Now look here. The 3D
we know that d orbitals generally have a high energy compared to s and p, right? You can see this clear energy difference. When we've reached the fourth energy level, the lowest orbital on the fourth energy level is the 4s, and we can now see that the 3d is higher in energy than the 4s. So the higher up you go, when you reach the fifth energy level, the sixth, you have overlap of orbitals. And orbitals in lower energy levels can be higher in energy than orbitals within a higher energy level. It's a bit confusing. It might be a bit confusing, but this is essentially what I'm trying to highlight, that the 3D here is actually higher in energy than the 4s. Now, let's take a look on how we know that orbitals exist. So, now experiments were done on some of these elements, and the experiment that was done involves ionization energy experiments. Now, what is ionization energy? Ionization energy is essentially the energy required for an electron to be emitted from an atom, the energy required for an atom to lose an electron, right? And we predicted a steady increase going across the group from lithium to neon. So if we should look here, going from lithium all the way to neon, we would expect to see a steady increase in ionization energy. But why? No, that would be the case because going from lithium to neon, you're adding protons to the nucleus. The nucleus is getting more positive. If the nucleus is getting more positive, therefore it would have a stronger hold on its outer electron, its valence electrons, right? Because positive attracts negative. Now, since it would have a stronger hold on the electron, it would be a lot harder for the atom to lose that electron. Therefore, the ionization energy would increase as you add protons to the nucleus. So we are expecting a steady increase going from lithium to neon. That is going from left to right across a period. But there were anomalies within the data. We did see a general increase in ionization energy, but there were kinks in the data in that we were expecting that boron would have a higher ionization energy than beryllium. And we were expecting that oxygen would have a higher ionization energy than nitrogen. We were expecting a straight line, but we did not obtain a straight line. We obtained something like this, where there were drops, and we didn't expect those drops. So the scientists at the time were wondering what was happening. Now, let's take a closer look at these three. We're going to analyze each kink. So let's look at beryllium, boron, and carbon, and then we'll look at nitrogen, oxygen, and fluorine, and to see what is actually happening. So, let me first see, an orbital is considered stable if it is completely full or half filled. Now, with that being said, let's take a look at beryllium. Beryllium has 4 electrons, and this is the electronic configuration, 1s2, 2s2. This is the valence energy level. The orbital at valence energy level is completely full, thus it is stable. With boron, the electronic configuration is 1s2, 2s2, 2p1. Now, the 2p is not completely full, nor is it half filled, so it is not stable relative to beryllium. With carbon, the p orbital, the 2p, is not completely full, nor is it half filled. But what can happen? You remember I was showing you the relative energies of these orbitals, and we said that the 2s is close in energy to the 2p. What can happen is an electronic transition from the 2s to the 2p, like this. You have the 2s, here, and the 2p right there, close in energy.
So an electron can jump from the 2s to the 2p to generate a scenario like this, where the 2s is half filled, therefore it is stable, and the 2p is also half filled with 3 electrons, thus it is stable. Once an orbital is full or half filled, it is stable. The half filled state might not be as stable as the completely full state, but it is still stable. So we'd end up with an electronic configuration like this: 1s2, 2s1, 2p3, and that would be a stable configuration, and this is termed hybridization. Hybridization is basically the mixing of 2 atomic orbitals to form something more stable. So let's take a look at the others. So with nitrogen, the electronic configuration is 1s2, 2s2, 2p3. So this is stable because the orbital, the 2p orbital, is half filled. With the 1s, with the oxygen, we have the electronic configuration 1s2, 2s2, 2p4. No, this is not completely full, nor is it half filled. Even if an electronic transition were to take place, it would still not be completely full or half filled. With fluorine, we have this electronic configuration with 2p5, but an electronic transition from the 2s to the 2p would result in a 2p6 orbital, which is completely full, and this configuration would be stable. Thus, since nitrogen and fluorine are stable and oxygen electronic configuration would be unstable, therefore oxygen would have a lower ionization energy than fluorine and nitrogen, because nitrogen and fluorine would not want to lose any electrons if it's already stable, because losing electrons might result in it losing its stability. So something that is unstable, like oxygen, might want to lose an electron easily or easier, and in the process thus becoming more stable. Now, let's take a look at the factors that influence ionization energies. Now, one of the main factors that influence ionization energies is the size of the atom. As the atomic size increases, the ionization energy decreases. Let's take a look at lithium and cesium from group 1. Now, lithium is very small. Cesium is very big. Therefore, the valence electron in lithium would be a lot closer to the nucleus. Thus, the nucleus would have a very strong hold on that electron, and it would be very hard to lose that electron from lithium. Whereas in cesium, the valence electron is very far from the attractive forces of the nucleus. Therefore, it would be a lot easier to lose an electron from cesium than it would be to lose an electron from lithium. Therefore, as you go down the group, the ionization energy decreases. You require less energy to lose that electron. But when you go up the group, the ionization energy increases. So let's take a look at sodium. So in sodium, let's compare it back to lithium. In sodium, the valence electron is a lot farther away from the nucleus than with lithium, because the lithium is a smaller atom. Here's sodium, here's lithium. So it's pretty easy to lose this valence electron. Once we lose this valence electron, we're now at the second energy level. So this energy level would go away, right? So the atom would get smaller. Once it gets smaller, it would now bear a noble gas electronic configuration. And it would be very hard to lose an electron from the 2s because the orbitals are completely full. So the first ionization energy for sodium is 495.8 kilojoules per mole. Now, the second ionization energy for sodium is 4,562 kilojoules per mole, signifying that to lose an electron from the second energy level would be very hard, because this energy level, the ion that would be generated would have a noble gas electronic configuration of 2s2, 2p6. Thus, the energy required to lose that electron would be very high. There's also the shielding effect. And the shielding effect is very similar to the size of the atom, in that it states that the effective nuclear charge being felt by the valence electron is affected by the amount of electrons in inner orbitals that shield the attractive forces of the nucleus. Now, I like to use lithium as my example. So, with a big atom like potassium and a small atom like lithium, potassium is using up 4 energy levels, lithium is using 2. Let's focus on the valence electrons. With potassium, there are 3 energy levels in between the valence electron and the nucleus, while with lithium, there's just 1 energy level. These energy levels serve as shields. It shields the valence electron from the attractive forces of the nucleus. Thus, if you have more energy levels, you have more shields. So, essentially, this nucleus is trying to hold on to this electron, but the forces have to pass through 3 energy levels, and each energy level that it passes through, it loses a bit of energy. Thus, with potassium, it's very hard for the nucleus to hold on to that valence electron. Thus, the ionization energy would be very small compared to that of lithium, where you would require a lot of energy to remove this electron, because it only has 1 orbital, 1 energy level that is shielding the attractive forces of the nucleus. So the nucleus is essentially holding on to that electron very strongly. Now let's take a look at nuclear charge. So the nuclear charge is essentially, the magnitude of the nuclear charge is affects ionization energy. The higher the nuclear charge, the higher the ionization energy. And we mentioned this earlier, that going from lithium to neon, the ionization energy is increasing. This is because the nuclear charge is increasing. We're adding protons from lithium to neon. Therefore, since the nucleus is a lot more positive, it can hold on to the electrons a lot stronger. Thus, it would be harder to lose those electrons. Therefore, the ionization energy would increase. And that just says, as we add protons to the nucleus, the nuclear charge increases. Now, let's take a look at aluminum. So, with aluminum, the first ionization energy is 577 kilojoules per mole. The second ionization energy is 1,816. The third is 2,744. And the fourth is 11,577.5. Now, let me first comment on the steady increase of ionization energy. There is a steady increase in ionization energy because there are 13 protons in aluminum and there are 13 electrons. So it's like a tug of war. The nucleus is pulling the valence electrons, the 13 valence electrons, towards itself, and the electrons are pulling back, right? Now, if we should lose the first one, therefore, we'd have less electrons. Thus, the 13 protons would be pulling these 12 electrons at a greater rate. If it loses another, the nucleus would be pulling even more. Thus, it would be harder to lose the third one. That's why the third ionization energy is higher than the second and the third. Because with each electron lost, the nucleus is pulling even stronger. Now, at the second energy level, that bears the electronic configuration of a noble gas, the noble gas neon, right? So it would be very hard to lose an electron from that electronic configuration. And plus, it would be, these electrons are a lot closer to the nucleus. So the nucleus is actually holding on to them very strongly. So it would be very hard to lose an electron from the second energy level. But imagine if they gave you this data without telling you that it was aluminum, you'd see that there's a gradual increase here and then a big jump. Now you'd say to yourself that this big jump seems like an electron was lost from maybe something bearing a noble gas configuration. Therefore, these ones must have been on the valence electron, and this electron might have been on the previous energy level. So you can think that, okay, this must be some group 3 metal, because group 3 metals have 3 electrons on the valence energy level. So that's how you would reason out a question like that. So for the overview, we commented on the size of, how the size affects the ionization energy. We commented on how the nuclear charge affects the ionization energy, and we commented on shielding. We mentioned that with size, as you go down the group, the size increases, thus the ionization decreases, the ionization energy decreases down the group, but ionization energy increases up the group because the atom is small at the top, thus the electron, the valence electron is closest to the nucleus, and it would be very hard to lose. With nuclear charge, we mentioned that going from left to right across a period, we're adding protons to the nucleus. The nucleus is getting more positive, thus it's harder for the valence electron to be lost. We spoke about shielding, and shielding is very similar to the size. Going up a group, the shielding decreases, thus ionization energy increases. That's because there's, with small atoms, you don't have a lot of energy levels that shield the valence electron from the attractive forces of the nucleus. Now, let's attempt some questions before our session ends today. All right, so the first question says, an experiment was conducted to determine the ionization energies of an unknown metal X. The following ionization energy data were obtained. The first ionization energy was 589.83 kilojoules per mole. The second ionization energy was 1145.45 kilojoules per mole. And the third ionization energy was 4,912 kilojoules per mole. Which of the following metals could X be? Now, this is how you would reason out this question. You'd look at this and say, okay, the first one was 589, okay. The second one was 1,145. And the third was, you saw a big jump from the second to the third, 4,912. So I would say to myself, okay, this looks like this electron was lost from something bearing a noble gas configuration. Therefore, this electron was lost from the previous energy level, the low n-1 energy level. So therefore, these two electrons must have been on the valence shell. Therefore, this must be a group 2 metal. And the only group 2 metal here is calcium. So the answer there is calcium. Let's take a look at the other question. Which of the following has these group 1 metals in order of increasing ionization energies? That is, the lowest ionization energy first and the highest ionization energy at the end. Now we have lithium, potassium, sodium, and rubidium. Now I know that lithium has the highest ionization energy there because lithium is the smallest. Therefore, the valence electron is closest to the nucleus. Thus, that valence electron would be very hard to lose. And they said that the lowest ionization energy first and the highest at the end. Lithium, A, is the only one that has lithium at the end, so the answer is A. Rubidium is very large, therefore it would have the lowest ionization energy of that series because the valence electron would be very far from the nucleus. Thus, it would take less energy to lose an electron from rubidium. The third question says, going down a group, atomic radius dash and ionization energy dash. Going down a group, the atomic radius increases and the ionization energy decreases. Because we saw with the group 1 metals where lithium was at the top and cesium was at the bottom, and cesium was very big and lithium was very small. Now, let's look at question 4. Let's look at question 4. It says, going across a period from left to right, the nuclear charge dash and the ionization energy dash. Now, going across a period from left to right, from lithium to neon, we're adding protons to the nucleus. Thus, the nucleus is getting more positive. Thus, going from lithium, going from left to right in a period, the nuclear charge increases. And the ionization energy thus increases as well, because it would now be harder to lose an electron from that atom. Now, let's look at the question 5. Question 5 says, going across a period from left to right, the nuclear charge dash and the atomic radius dash. Thus, going across a period from left to right, the nuclear charge would increase, but how would that affect the atomic radius? If the nuclear charge increases, therefore, the atomic radius would decrease because the nucleus would be pulling the outer electrons closer to itself. Thus, the answer would be D. Now, that's the time we have for CSEC chemistry, CAPE chemistry, sorry. You can watch back today's lesson on onespotmedia.com and JNN between 4 p.m. and 7 p.m. Class time will be tomorrow at 9:45 a.m. right here on TVJ. And remember, if you have questions, send them to the Television Jamaica's Facebook page or on Instagram at television_Jamaica using the hashtag TVJ class time. Until then, keep safe.